Today's micronutrient history lesson is all about zinc, and we're going to go back in time to see how this shiny metal has been discovered and rediscovered over the years. So I've got a little bit of colorful history on zinc, noting first that the Romans and the Greeks were aware of zinc way back in 27 BCE and beyond, and they actually didn't really use it much, but we know that they knew about it. And we know that it was used in India in the 1100 to 1500s. And in 1745, the British East India Company had one of their ships wreck off the coast of Sweden, carrying Chinese zinc ingots, like metal bars, and they have actually recovered some of those. So we know that it was being traded at that time. And it was recognized as a metal in 1746 in Germany. And in 1869, it was recognized essential for microorganisms. In 1926, it was recognized as essential for plants. And then in 1958, recognized as essential to poultry. It wasn't until 1963 that zinc deficiency was recognized in the Middle East and Iran, when a researcher was presented with a 21-year-old male who resembled a 10-year-old male with growth retardation, hypogonadism, immune dysfunction, and many other issues. And this was the first time that they discovered that zinc was actually the cause of these problems with growth and retardation. And actually, many researchers kind of doubted the role of zinc deficiency until more research came up in the next decade. So it wasn't until 1974 that the American Academy of Sciences declared zinc as essential for humans and established the RDA, which was the same as the RDA in 1989. You can see that the RDA, when it's now converted to the DRI, is a little bit lower. There is also a DRI for pregnant and lactating women, and just an AI for infants. And in 1978, the FDA did have to mandate zinc be added to TPN after several cases cropped up with zinc deficiency on TPN patients. The requirements for zinc are based on factorial analysis of metabolic studies of zinc absorption. Zinc absorption is defined for this purpose as the minimum amount of absorbed zinc necessary to match total daily zinc losses. The dietary intake corresponding to this average minimum quantity of absorbed zinc is the EAR. So for food sources, most bioavailable is found in animal products, especially red meats and seafood. And most of US citizens get this from animal products as well. 30% of our dietary zinc is from cereals, some of which are fortified. And other good sources are poultry, pork, and dairy. And you can understand that zinc is therefore found complex with nucleic acids and amino acids within protein, requiring a hydrolysis in an acidic environment for absorption. Plant sources also have some zinc, but they're less bioavailable due to those darn pesky phytates and oxalic acid, just like many of our other nutrients we've talked about. And then we also have endogenous zinc coming from pancreatic, intestinal, and biliary secretions released into the GI tract with food consumption and can be reabsorbed if we need to maintain that zinc homeostasis. So there's several key functions of zinc. The main umbrellas are catalytic, structural, and regulatory. So let's jump into a few of these. So I just wanted to say that magnesium is really taking the show as a cofactor for over 300 reactions, but not so fast, because zinc, while not a major mineral, is a key trace mineral and is also required in over 300 enzymatic reactions. So it affects carbohydrate, protein, nucleic acid, and lipid metabolism. You can see here its role in the superoxide dismutase antioxidant, along with copper. It's also key in alcohol dehydrogenase, kinases, nucleases, and many other enzymes. So under the structural umbrella, it binds to over 2,000 transcription factors as a zinc finger, affecting gene expression and therefore affecting physiological function. And we also need it to bind protein to DNA. You can see in the example here of a zinc finger binding to a gene that affects keratinocyte differentiation. And on the right side of the image, you can see B, C, and D are the downstream effects of this gene binding with zinc to enable that expression. So lastly, some other key functions are maintaining cell membranes, insulin transport, which you can see on the right there. that allows us to help maintain glucose homeostasis, maintaining basal metabolic rate, cell survival, and immune function. It's a second messenger for immune cells and essential for cell-mediated immunity. So with zinc deficiency in children, you can see that there's growth retardation, skeletal abnormalities, poor wound healing, diarrhea, skin rash, dermatitis lesions, and delayed sexual maturation. In adults, we see anorexia, diarrhea, lethargy, vision problems, alopecia, impaired immune function, protein synthesis, and wound healing that are also impaired. And you can see in the left in the picture some people that are more prone to zinc deficiency, but also we see deficiency in older adults with lower stomach acid, those taking chronic thiazide diuretics, GERD and heartburn meds that lower acid that all reduce absorption, as well as chronic alcoholism and malabsorptive disorders. For toxicity, this doesn't likely happen from food sources, but mostly from supplements. Acute toxicity, you can have that metallic taste, headache, nausea, vomiting, epigastric pain, cramps, and bloody diarrhea. For chronic supplementation, you can actually alter the copper and iron status. And this is why the upper limit is 40 milligrams a day from water, food, and supplements because of the effect it has on blunting copper.